So similarly, to improve the wettability, we can go for some of the coating, especially copper coating over the boron carbide particles to improve the wettability. And these aluminum alloys are also used in the armors, lightweight armors, especially SiC particles are embedded into the armors, and because it absorbs energy when a bullet hits on that. So they incorporate these ceramic particles, and even we can make a functionally graded armor like this. One side we can have a SiC rich layer, and back you can have an aluminum backplate. The advantage is that when a bullet hits the other side, this aluminum SiC composites will absorb energy through fracture mechanism, and the pure metal will absorb the impact of the bullet by what you call the deformation mechanism. So this type of functionally graded armors are being also made. So these are the typical plates which we have made at the CSIR NIST. And the second technique is the semi-solid processing. Semi-solid means we have a semi-solid region. So there's some alloys which will melt at high temperature, around up to 615 or 6, especially you take aluminum, the melting point is 660. And if you are having an alloying additions, normally because of the colligative properties, there's a depression freezing point. If you take a 356 alloy, the melting point is around 615. And there is a solidus range also that is around 577. So in between 577 and 615, there is a partially melted region which is called semi-solid. You can stir it just like a curd or butter. So at the temperature, you can add the particles. So that because of the presence of the alpha particles, the dispersion will be good. So this process can be used to make the components, especially dispersion. And this can be used to even make composite with very fine dispersion. Even the nano-sized particles can be made, and this can be made to, and more than that, the minimum interfacial reaction and more uniform dispersion of the particle is also possible. The next process is called the infiltration process. Here what we take is that we make a porous preform, SiC particles or any particles, we make a preform, we preheat the preform, place it in a die in a press, then we pour the metal and apply the ram. So then the metal get infiltrated, and either we can have a vacuum or pressure infiltrated vacuum and pressure or reactive sintering can be made. So this fuse casting process is a combination of casting and forging. So there is a high pressure die casting where when you pour the metal into there, what happens is that the plungers will come and hit and it gets filled. But here the fuse casting, we apply the pressure till the solidification happens, and the components will be of very high strength. That means highest mechanical properties are achieved in the cast project, and these are near net shape with nearly porous fit. So this is the concept which we use to make this infiltration also on the products. So there are direct fuse casting and indirect fuse casting. Direct means directly the pressure comes into the component. Here we will having a feeder system to which the force is applied through the cast product. So there are a lot of advantages for this fuse casting, especially no shrinkage, porosities or gas porosities, fine grain structures, turbulence and fluidity effect is minimum and large. However, the limitations are high initial cost, limited size and shape complexity, and the tooling cost is also very high. And if you see the advantage is that suppose you take an aluminum alloy and fuse cast, the advantage is that the sand cast aluminum alloy will have around 226 megapascal, that is ultimate tensile strength. But when you fuse cast it enhances to 347. So you can see all the properties are higher. Either it's a yield strength or it's a tensile strength or the elongation, all are higher than that of a sand cast or jade. So this is mainly due to the refinement of the grains. So this is sand cast such a very cold sand. When you have a pressure applied casting, you can see the alpha phase and all the things are very much refined to a greater extent. So this we had studied a lot of alloys, and we observed that compared to the gravity and fuse cast, grain size is reduced. So that means the alpha grain size is reduced, the dendritic arm spacing, the arm spacing between these two dendrites also getting reduced remarkably. So this will reflect in your properties. For example, you take this aluminum silicon-based alloy, you do gravity casting at the heat-treated condition, the ultimate tensile strength is almost 275. And you can see this fuse cast heat-treated is 385. So more than 100 megapascal increase, the yield strength in the S cast is higher. Even the percentage elongation is slightly affected because of the skews cast and grain. So, however, the strength properties and very much getting, and the component produced is also highly integrated. And we have a pilot scale skews casting facility at CSIR NIST, where we can have a 100 kg melting furnace, and there's an auto ladler system. So this will come, this ladle will take the metal of required quantity, pour into this one, and there is a die like this, and the metal will press into that, and once a component shape is formed after solidification, then we remove. And normally we have the capacity of the casting weight is 1 to 5, and the product size is 800 by 800, and the thickness is around 1.5 mm. So here we can see that this scroll compressor plates are being made by our facility, and it's supplied to Atlas Copco, Belgium. And the scroll compressors are mainly used in the train and other automotive systems mainly. So the requirement is here high strength and high thermal conductivity and lightweight is the requirement. So that's how we had made this, and these are all the selected properties of the aluminum alloys, which I think I will not go. We also had done this rare earth added aluminum alloys, because rare earth addition to aluminum alloys will improve the strength of the material by reducing the grain size. And here, if you reduce the grain size, then there is an increased hardness, increased wear resistance, improved cast stability, elevated temperature stability, because of the formation of high temperature phases. And because normally the aluminum have low temperature phases which is formed. But if you have for example, it's aluminum scandium alloys, Al3SC is a highly thermally stable phase. Similarly, in the case of cerium alloys, it's Al7Ce3 and Al11. All these alloys have highly thermally stable high temperature phases. Maybe I will not go into the detail of that. So you would take one example is that scandium. When scandium is added to aluminum, for example, if you have normally, as I hope you remember that these structures are made of 2000 series alloys, an aluminum copper alloy with heavy weight. And if you are able to remove this copper with aluminum magnesium scandium alloy 5000 series, directly you have a reduction of 4 to 5% of the weight savings. And more than that, this particular alloy is having exceptional weldability, excellent damage tolerance, and better corrosion resistance than that of the 2000 series. So these types of alloys are also being used, and strength is also high. So just I will show an example. For example, 4 magnesium with 1 scandium, you can see that UTS is 525 and the yield strength is almost 420. So you can see enhanced properties. So the addition of scandium reduces the grain structure. If you don't have scandium, you can see very cold structures. And addition of scandium almost with the 0.3%, it reduces the grain size to a greater extent. So thereby it improves the properties. And the formation of Al3SC precipitates also strengthens the alloy. So these are these Al3SC precipitates which is getting formed. So we had done some rolled sheets. We had indigenized this plate and transferred this one. So you can see during rolling the structure get elongated and fine, and this has very high strength capability. This is a 1 meter length rolled sheets. We also do this recycling of the alloys, because you know that we cannot always have virgin materials too. So whatever the used spent radiators or structural building materials or engine components, anything is taken, then it is being again remelted and converted to useful alloys. So this is a skews casting I had just informed earlier. How it is done this, how this preform is made. You have the particles, you have the polymer or something, and binders. Then you have to make a green compact, cinder it. You will end up with porosity, and this porous body is kept inside the die and infiltrated. So this porous body looks like this. It's a green cindered body, and after leaching, with salt we can leach out. If it's a polymer, we can burn it out. You will get a porous body like this with all the SAC reinforcement, and you can get a reinforced composite of this type of. So here we can see that the particle size is very much finer, and it is very well distributed throughout the matrix. You can see the 2000 series of alloys, and this is and you can also see that the heat treatment shows as you increase the particle size, the hardness also getting increased. And this can be used for varieties of application, starting from arbors and as well as in thermal management. And one of the typical experiment is that this SiC particle has high thermal conductivity. Because of this, we had added almost in aluminum silicon alloy, we had added 68% of metal, so silicon carbide, and infiltrated the material. And we observed that the hardness is around 210 BHN, and the CT, one of the requirement in an electronic thermal management system is low CT and high thermal conductivity. So we observed that so CT is very less. Normal alloys, aluminum alloys have more than 20 ppm per degree C, but this one is having very low CT, and thermal conductivity is 176 and good strength and modulus. So this is our light compact aircraft, which has a digital flight control computer systems. And these digital flight control computer systems have thermal management gates. All this will be placed. You have a printed circuit boards and all electronic system and control process. Everything will be mounted on this. So this will be again placed on this DFCC. And this DFCC have the take care of the full control of the aircraft, maybe communication with the ground station, the operation of the whole aircraft, then attacking the targets with the missiles which is mounted in the aircraft, or identifying the missiles which is coming to hit the aircraft. And all this is controlled by this whole digital flight control computer systems. And this is a very critical components when there is a lot of heat generated in the electronic systems, so it has to be completely dissipated. And main requirement is high thermal conductivity and low resistance. So this is an SiC particles, and we have developed almost 30 components and transferred to DRDO, Defense Research Organizations, for their application in the aircraft, and it's under different levels of study. And here we can see that we can use different sizes of particles. Maybe so this pure aluminum, then we can see that it's a 10 micron, 20, 30, 50, 75, and 110 microns. And we had evaluated the thermal conductivity, and we observed that the larger the particle size, thermal conductivity is high. The reason is how this thermal conductivity happens is in the metal, there is free electrons which will transmit the thermal conductivity. The heat is getting, which is a quantized packets of particles, so that transfers the energy, actually the heat energy, so that conducts. So if you have a larger particles, there is no inhibition, and if you have very much finer particles, there are a lot of inhibition and scattering, complete scattering of this either it's a phonon or it's a free electron, so that conductivity is getting reduced when compared to. So this preferably it is a larger particle is better, but the measurability and other factors also required. So normally we go for this 50 to 75 microns, which is having around 176 watts per meter. So apart from silicon carbide, we can even have graphite, which is having. But what are the disadvantages? Graphite is anisotropic. So normally thermal conductivity in this direction will be very high, and in this direction is very low, because you can see that the thermal conductivity or electrical conductivity in the graphitic layer is very good. So you can see, so it will not conduct. So this is very much clear here. So if you have in Z direction, that is the graphite aligned direction, you have a thermal conductivity of 316 watts per meter Kelvin. Same thing if you have almost in the other direction, so you can have very low thermal conductivity. So this is an anisotropic properties. Again, we tried with other type of reinforcement. For example, we have the diamond particles. We procured natural, synthetic, and metal bonded diamond particles, made the composite. You can see that very clearly the distribution of the particles here. And this is the microstructure of the metal bonded very crystalline diamond particles, which is again embedded in an aluminum matrix. And we had evaluated all the thermal properties of this materials. So even this diamond is stable up to around 800 to 900 degrees C in air atmosphere. And this, when we had evaluated the thermal conductivity of these compounds, we observed that the metal bonded diamond particle shows 479 watts per meter Kelvin. So your aluminum is 154 or 134 at as-cast conditions, getting increased to 179 when it is a synthetic diamond, 250 to it's a natural diamond, and 479 when it is a metal. So the structure of the diamond particles and the interaction with the aluminum makes. So you can tailor the required thermal conductivity of all these materials. So similarly, we had also used this carbon fiber. I think I'll not go to the very much detail. I will just quickly skip on because the time is already 7:30 is over. So again, we had used these fibers, which is infiltrated with the liquid metals. Because of the self-lubricating behavior, this can be used in the pantographs. Self-lubricating means it will not get weird. So there will be a lubrication layer which forms. So this is for alloy, getting weird very quickly. But for composite, it is not wearing quickly. So that's because of the formation of the lubrication layer because of the carbon fiber, which forms at the interface. We had also studied this graphene with very low this percentages. I think I'll not go into the details of the study, but I will sum up the observations what we got it in the. So this graphene addition also enhances the thermal conductivity. For example, 154 to 224 for 356 alloy. The wear resistance is again very high, similar to that of carbon because of the self-lubricating behavior. Here we can see this is an mechanically mixed layer which is formed at the interface, which will not allow to further wear. It will just give a lubrication layer when there is a movement of any automotive or aerospace component. So overall, the thermal conductivity of this aluminum graphene is higher, and hardness is also getting improved. Tensile properties and all the properties are getting enhanced. So just some of very critical or important components of MMCs are in automotives. We had seen a wide range of automotive components starting from brake, rotor disc, cylinder liners, intake exhaust valves for railways and automotives. Again, these are all automotive components which is being used. So again, brakes and other systems. So this is a component brake rotor disc which is used for the high-speed trains in Germany, where you can see all this discs are fitted, mainly the lightweight and high friction of this one. And the composites are also used in the recreational purpose. It is used in the space application, especially the space shuttle orbiters, even the waveguide antennas, the fittings, especially in spacecrafts for thermal management application as such. So different components are being used in different thermal management applications in the electronic packaging systems. Even the fighter aircrafts also, for example, in the F-16 aircraft, the ventral fins, they use the 6000 series alloys with almost 17.5% of SiC particle, which is made by powder metallurgy process with DWA composites. Again, aluminum SiC composites are used for thermal management applications. Fan exit waveguides, again, they use this type of composites. This Blisk, which is used for fighter aircraft engines. This is a titanium composite Blisk. And this is the one which I was telling in the initial. The whole structure is made of GLAR fiber, that is glass fiber reinforced aluminum alloy composites. What do they do? 0.38 mm of a aluminum alloy sheets, thick sheets, which is laminated with glass fiber reinforced resin or a carbon fiber reinforced resin, and then it is led to formation of a laminated composite, and there is a 15 and between 15 and 30% of weight reduction is there and improves the properties. So this is being used in the A380 aircrafts and many other aircrafts of Boeing and Airbus. They use these type of structures. So to summarize my talk, lightweight materials play a critical role in the weight reduction of both automotive and aerospace sector. Aluminum is one of the most important light metals, which finds potential application in these sectors. And there's a lot of scope for developing. You can see that either alloys or composites. A lot of scope is there to develop new materials which can reduce the emissions, which can be used in the electric vehicles. And in India, the Atmanirbhar Bharat, that's import substitution, self-reliance, is major thrust, has given major thrust in lightweight materials. However, a strong industry and R&D linkage is required for the development of these materials and applications. And we can use these materials or components can be made by in the additive manufacturing techniques, all those materials. Since a lot of lectures are in additive manufacturing, I thought I'll give an most of application oriented of the lightweight materials and so on. Thank you very much for your patient hearing, and best wishes to all of you. I think I will stop share and I can take a couple of questions if somebody has some doubts. Thank you very much. So any doubt, you can either put in chat box or you can tell. Oh, there is one question. Glare composite. So more on glare. Glare is, as I mentioned in the last slide, I think I will again take that slide once again. I can share you. So glare is glass fiber reinforced aluminum composite. GL stands for glass and AF stands for aluminum and it's reinforced RE. So here, this is made by almost 0.38 mm or 0.015 mm thick sheets of aluminum alloy and glass fiber, which is resin bonded. Resin means it is epoxy resin. So you have a glass fiber bonded resins, then you have the thick aluminum sheets, then it is normally compacted or rolled. Mostly it's compacted. And because of this laminate is formed, and this laminate is used because normally the outside structure will be completely of aluminum. And inside, I think if you see this, all these buildings, they use this aluminum composite panels. It is similar to that of this aluminum composite panels will have both the sides to the aluminum sheets, and inside you will have a light foam structures, which normally gives the reduction weight and the overall stiffness and all other properties. So same concept is used, but here we use either glass fibers or a carbon fiber. Glare means it's a glass fiber reinforced, but other type of laminated fibers is also there. So they are used this one. So this can be used. So this whole aircraft structures is used by this material, especially the glare fiber composites. I hope the person has understood. So there is no other questions. If any question is there, I think you can just type in the chat box or I'll wait for a minute. And if nothing is there, I think the organization can conclude. I think thank you for all the people, those who had given that it is very useful and a very good session. And even you can type, so what you missed in the talk, what I can add in the subsequent lectures, that also it's feedback you can give. No problem.
Sir, I've got one question. I'm Dr. Puneet Mangla.
Okay.
When we talk about lightweight metallic sheets and all, as you explained, very nicely explained about the applications of these materials, lightweight materials.
Okay.
So, can you relate it with the, like aerospace industry, manufacturing of the parts related to your additive manufacturing in broad?
So you want to link to additive manufacturing?
Yeah.
Yeah. In additive manufacturing, aluminum, tin, silicon, magnesium alloys. I don't know whether Dr. Anil has explained, because Anil, Ravi, all we know that all are very close friends and we are collaborators too. They might have explained. So this aluminum alloy powders are being made because different techniques are there. If you take the powders of this AL10Si silicon alloy, this alloy is being used to make different types of components. And I don't know how many of you have seen, apart from this, even titanium alloy based components are also used. And recently, for our this Agni-cooled engines, mostly they use super alloys, which is nickel based alloys. But specifically for aluminum based alloys, especially this aluminum tin silicon, different now new powders are also come with the difference. So they can be additively manufactured by this laser bed technique or other type of welding technique. I think maybe Dr. Ravi might have explained about the welding systems and additive manufacturing using those deposition techniques, or maybe the direct energy deposition, which Vinod might have explained to you. So all these techniques, we can use this aluminum. But if it's a base laser bed technique, then you have to have the precursor aluminum in the form of powders. If it is welding, that type of deposition, then you have to have the wires. And if it is a fusion type of DED, means there's a again the metal powders or even the wires can be used. And all these places they use this type of powders, and many components can be made by this additive manufacturing techniques. And even some of the components which I had shown also, if it is smaller components, definitely we can make it with the additive manufacturing techniques can be used. But there is a limitation that the particle size of the powder used maybe around to from 35 to 100, or that's the range, because that will give better processability. And some of the alloys is not possible to do the additive manufacturing. So that limitation is still there. And sometimes some achieves the properties equal to the wrought alloy, and so some cases it doesn't. So these are all we have to do. Some selected alloys are being currently made and used in the aircraft and other parts.
So mainly that means like powder-based technique is mainly used in this additive manufacturing for using aluminum as a material.
Yes.
Powder-based technique is mainly used for aircraft industry parts, right?
Yeah. Mostly they go for smaller parts only. Not huge parts they are not making. Because huge parts and structures they make with rolled sheets and they do welding. So if you have a and mostly because the cost effectiveness of this additive manufacture product is also high, and if you have minimum number of samples, we can make it. But the problem is sometimes we will not have the properties of what either a forged or a rolled or a cast structure or a skew cast structure is getting. So that difficulty has to be solved. So there's a lot of scope for doing research on these areas. But even the studies have shown that some of the places they had used this additive manufacturing, which gives the properties which is equal to that of either a cast structure or a force structure and so on. So but however, the alloys which can be used for additive manufacturing is very much limited.
Hmm.
Hope
So
I had.
Basically, the printing of aluminum is difficult actually, as far as I
Printing
know.
of aluminum is
A bit
yeah,
difficult.
printing of aluminum is definitely difficult when compared to that of other metal, either it's a titanium or nickel based alloys. One of the problem is the reflectivity of laser with aluminum is very high. That also is another reason. Then the melting and fusion is also very difficult. But now they already made a lot of compounds using. If you, I don't know, Anil has covered it or not, but I had not touched upon this because already they made it given. But when compared to that of superalloys and other things, it's difficult, but it is still possible, and people has made very successful compound out of aluminium also.
Okay.
Okay, sir. My question is, what are the tools and the softwares are used for weight reduction? And can you highlight on topology how it is related to weight reduction? Topology optimization.
No, topology optimizations means what actually you are telling? The automotive components mainly they use this lightweight metallic metals, either aluminum, titanium, or magnesium, mainly because of the reduction in the weight reduction the density. So automatically it will reduce the component weight. That's why they use, and also the performance. For example, if it's a wherever you want radiators or some other places you want the high thermal conductivity, then they use aluminum because it has a highly thermally conductive next to copper and silver when compared to any other metals. That's why they use. But topological optimization, I think I cannot understand what you mean actually.
Sir, topology optimization with reference to the weight, weight reduction.
No, weight reduction means for structural things.
Yes, yes.
No. Normally, if you see that any aircraft or automotive components, no. So all the components cannot be replaced with aluminium because the aluminium melting point is around 660 and the steel is around 1300 plus. So wherever the very high temperature requirement is there, high temperature stability is required. Those places definitely you cannot use the aluminium. Again, the places just like very high strength is required, because this aluminum alloys will have strength up to maybe around 600, 700 MBA. And as the temperature increases, the strength will come down. And maybe, for example, 250 degrees C or 300 degrees C will have an effective strength. But steel and titanium will have very much high temperature resistant strength. So wherever the component is exposed to heat, temperature, those places definitely you have to use the steel and other materials.
Right, sir. Thank you. Thank you.
Thank you.
There is another question in the chat box.
Yeah, one more is aluminium is difficult to print. I think already the previous participant also asked. Definitely the aluminium is difficult to print, and only the way to do better is find very good aluminium alloys. So as I mentioned, aluminium, tin silicon, magnesium alloys are very much optimized. So similarly, we have to do research and find out which are the good aluminium alloys which can be printed, and similarly the best processing routes. For example, the direct melt and deposition routes also can form, because a lot of welding is there, no? But it doesn't give the strength that of the rolled structures or a forged structure or maybe a cast structure, because of this. Most of the things are all solidification process, because whenever you do a laser bed melting and deposition or by additive, other type of additive manufacturing and direct deposition techniques, everywhere the metal gets melted and again get redeposited over there. So it will lead to the formation of a what you call a solidification as cast structure. And then you have to do all pre-processing. Then surface preparation is required. Oxide formation has to be avoided. So a lot of things are there, but mainly developing very good powders in the case of laser bed, or the fillers and the wires for the additive manufacturing. Then process optimization. All this has to be done, and there is a good scope for making. And many of the times they go for highly intricate shapes. Currently, many of the structural sheets and other things, everywhere it cannot replace. Wherever the sheets is used, we cannot replace with additive manufacture. But just like components of small heat sinks, or whichever is very complicated in shape, or any other engine components which is most complicated. So wherever, whichever places where we can definitely replace with aluminum. But a lot of research has to be done. Okay, thank you. So any other questions?
So can you share your contact details or email ID something?
Yeah. I think I will put here. My email ID is tpdrajan@gmail.com. So I think everybody can see, and my mobile number is 944-703-5439. And even if you Google it out also, you will get this detail. And I think already in your pamphlet, my full description is there. So this is my personal Gmail, official email ID is another one, but you can contact either this through this phone number for any help or things. I can do it. Absolutely no problem.
Okay, thank you. Thanks a lot.
Thank you.
Thank you, sir, for your informative session. To conclude the first session, I invite Mr. Janu, Assistant Professor, Bethlahem Engineering, to deliver the vote of thanks.
Yeah, good evening, one and all. On behalf of the Department of Mechanical Engineering, Bethlahem Institute of Engineering, I am honored to deliver the vote of thanks for our 6-day online faculty development program on additive and manufacturing. First and foremost, my heartfelt thanks to our chief patrons, director, principal, dean academics, convener, program coordinator for their continuous support, for approving resources, and for empowering the faculty and organizers to run this FTP smoothly. Now, a gratitude to our resource person for this session, Dr. TPD Rajan. Thank you for your insightful session on metallic additive manufacturing. Thank you for making this session meaningful and memorable. We deeply appreciate your commitment and dedication. Thank you, sir. I would also like to thank all participants, organizers, and supporters who helped make this program a success. Once again, our heartfelt thanks to all for your invaluable time and knowledge. Thank you very much. Thank you.
Thank you, sir.
So thank you for invitation.
Okay, thank you, sir. Okay, the participants, sir.
Okay.
Next season will started
I
sharply.
can talk off, no? I will.
Okay, sir. Okay. Okay, dear participant, the feedback link is shared in the chat box. The next season will start sharply at 8 p.m. So be on the online. Okay. Sir.
அருஜர்மன்
Hello, sir.
அருஜர்மன் அதை பிபிடி டிஸ்ப்ளே பண்ணுங்க.
Okay.
அஜித் சார்,
ஆ,
அஜித் சார்,
சொல்லுங்க.
என்ன போட்டோ வீடியோ எல்லாம் காட்டுறீங்க?
பயங்கரமா இருக்கா?
ஆமா, நீங்க
ஆ?
presentation வேணும்.
என்னது?
Good evening, everyone. Let's start our second season. To start our second season, I invite Mr. Aziz, Assistant Professor, Department of Mechanical Engineering, to introduce the resource person.
Good evening, everyone. It is my great honor to introduce our esteemed chief guest, Dr. Pratik Saxena, Assistant Professor, Grade 1 at the School of Mechanical and Materials Engineering, Indian Institute of Technology, Mandi. Dr. Saxena is an accomplished researcher in the field of additive manufacturing with impactful contribution to continuous fiber reinforced composites and advanced manufacturing process with the sustainable tooling technologies. He holds a PhD from the Technical University of Denmark and has enriched his expertise through the research engagement in Germany, Denmark, and UK. With more than 36 journal publications, international patents, numerous sponsored research projects, and H index is 20. Dr. Saxena stands as a leading young scholar in his domain. He also serves as editorial boards of reputed journal and has guided several research scholars at IIT Mandi. We are privileged to have such a distinguished academic and innovator with us today. And we warmly welcome Dr. Pratik Saxena to grace this occasion with his presence. Thank you.
Thank you, sir.
So, first of all, very good evening to you all. Thank you very much for the wonderful introduction. I would first like to thank Dr. Das for inviting me to deliver this talk today. And I will quickly share my slides and then we can start with today's discussion. Okay, so I hope my slides are visible now.
Yes, sir, it's visible, sir. Visible, sir.
Okay. And let me flip through them. So please confirm if you see the next slide.
Yes, sir. Yes, sir.
Perfect. Okay. So we can start with today's discussion. So the topic for today's discussion is extrusion-based metal additive manufacturing for lightweight structures. My name is Dr. Pratik Saxena, and I'm an assistant professor at IIT Mandi. So before we go into the depth of this topic, we need to pick up some keywords from here. So what are the different keywords that are present in this title? First is that we are going to talk about metal additive manufacturing. Second is that we are going to talk about extrusion-based metal additive manufacturing. So in which the metal printing is happening with this particular type of technology. And the application for this will be lightweight structure. So these are the three different paradigms that we are going to discuss in today's lecture. Okay. So this is our very beautiful campus of IIT Mandi. We are located in Himachal Pradesh, and here you see that we receive snow every now and then. So coming to the topic, how to manufacture lightweight structures in metal using additive manufacturing. You see, lightweight structures have got a lot of applications, be it in aerospace, be it in space structures, for automobiles, and several other applications where lightweight structures are desired. And how to create them using additive manufacturing is today's question. So if you do a little brainstorming, there are several uh, candidates, there are several options using which we can 3D print in lightweight structures. The first and very obvious choice is that we should choose some lightweight metal alloy. This can be one possibility, that you can argue that we can perhaps choose something like aluminium, and we can design our structure in that. This will make our structure lightweight. The second option could be that we can design something like a hollow structure, so a structure which might have an optimized wall thickness. So this will also reduce some weight. Someone can say that we can also use some graded structure, something like functionally graded structures. We can vary the density throughout, or we can have a material composition, a different material composition throughout the structure. So that is another possibility. Someone can say that we can also use topology optimized structures. Okay, with the help of topology optimization process, we can also perform lightweightedness. Okay. Another possibility is that we can incorporate lattice or cellular structures such as gyroid, honeycomb, etc. for internal geometries. So lattice structures or cellular structures, I hope you might be familiar with what they are. So inside of the structure is partially empty, and there exists some kind of pattern inside the structure. So that is called as a lattice structure. So to give you an example, this is an example of closed lattice structure. So this gear might look perfectly solid from the outside, but if I take a cross section, here I can see that it has got some pattern inside it. Okay, so from inside, that this is not completely hollow. There is some kind of pattern that is embedded in it inside. So this pattern is not essentially for the aesthetic, but this also has some role in the aesthetic properties of the overall strength of the structure. Not only for the aesthetic, but also the overall mechanical properties can be enhanced by having different types of lattice structures. Now the question is that is the most popular metal additive manufacturing technique, which is laser powder bed fusion, a good alternative for creating this structure? Okay, if I give you a task that you have to 3D print this in metal, this is the first and obvious choice that will probably come to your mind, that let us use some laser based process, let us use some selective laser melting based setup using which we can 3D print this structure. But the question is that is this type of process where the lasers are being used and there are metal powders, is this a good alternative or not? The answer is no. And I would say that you take a couple of seconds to think about that why LPBF is not a good alternative for creating these structures. I will also discuss in more detail in the next slide, but just give it a thought that why such a structure cannot be easily made with the help of laser powder bed fusion. The challenge is that the metal powder which we use in laser powder bed fusion, they get trapped inside these closed lattice structures. Okay, because the structure is closed from both the ends, there is no provision of removing those metal powders. And if the powder gets trapped inside the structure, then it increases the overall part weight, which entirely defeats the purpose of lightweightedness. Okay, so this is one problem. Another problem that you will probably face is that if you have some kind of support structures inside closed lattice structure, they are also very difficult or impossible to remove. So manufacturing closed lattice structure using laser powder bed fusion is very complicated. Now, this is the overall context of today's discussion, that if the most popular technology, which is the most popular metal additive manufacturing technology, which is laser powder bed fusion, cannot make these kind of structures, and on the other hand, we are saying that such kind of structures can help in lightweightedness, then what is the solution? These structures are not new structures. These are very common structures which we use in polymer 3D printing. There are hundreds of infill patterns, hundreds of lattice structures that you can use for while making your structure using polymer parts. Okay, so what is the solution? And to understand the solution, you first need to look into the families of the 3D printing process. Now, I'm pretty sure that my other colleagues, the speakers might have shown you a chart similar to this, that these are the different 7 families of the 3D printing processes. So 3D printing is not a single process, it's a family of processes. And there exist processes like wet photopolymerization, material extrusion, material jetting, binder jetting, powder fusion, direct energy deposition, and sheet lamination. I'm not going to go into the details of all these things, but if I ask you to look into this chart, and if you have to identify that which is the most commonly used additive manufacturing technology, not talking about metals, but in general, which is the most commonly used additive manufacturing technology that you might have seen, in your lab, in your workshop, or you might own a 3D printer based on that technology, the answer will be material extrusion based technology, which is FDM. So again, there are different material extrusion technologies which are available. FDM is one of the technology that we are going to talk about today. So FDM, like we know, is a very common technology in additive manufacturing process, and most of the printers that you might have worked, the cost-effective printers, they all are based on FDM process. But again, FDM process is used for 3D printing parts in polymers. The discussion for today is that how you can 3D print metal using this particular technology. So what I'm going to teach you in the next few slides is that how you can combine the easiest known process, which is the FDM process, for 3D printing of metal parts. Because if we understand that how we can modify our existing printers for 3D printing metals, it not only solves the problem of lightweightedness, but it will also solve the problem of cost. It will bring down the cost significantly. Now, just to give you some numbers, like if you want to say that I want to buy a laser-based 3D printer, you want to buy an SLM setup. So that setup will easily cost you something around 1.5 CR. The cheapest one will cost you 1.5 CR to 2.5 CR. And a good one might cost you something around 3 to 4 crore, 5 crores, or even higher. And then another constraint in these kind of setups is that if you have to print a very small part in metal, you have to fill the you have to fill in the setup with at least 8 to 10 kilograms of powder. So in some setup, they say that you can still fill it with 5 kilograms or 6 kilograms of powder. But imagine you have to make a part which will weigh something like 100-200 grams, and for that part you still have to fill it with the powder, which is something like 7 kilograms or 8 kilograms. So you have to invest first of all in buying that much amount of powder, and secondly, you will not be able to print a part in a different material until that entire powder is consumed. So the machine needs to be emptied, and then it needs to be refilled with another kind of powder. So this is a challenge. So even though if you don't own an LPBF based printer, if you go to a vendor saying that, can you please print a part for me in maybe stainless steel or titanium, they will probably charge you something around maybe 25,000 to 30,000, even 40,000, depending on which material you are asking. And the size of the part will be very, very small. A very small part like this can easily cost you something like 25 to 30,000. And if you have to print it on your own, then you have to invest a lot on, first of all, on the machine, and then on the raw materials. So this is another challenge, that see, if it is not only the lightweightedness that is a problem, but also the cost is the problem. Now, a good thing about FDM is that we all understand FDM in the most, in the most detailed way that is possible. If I have to compare it against all the other processes, FDM is the most well-known process. Okay, very well understood and very easy to handle, and again, it is very cost effective. So the question again remains is that how to 3D print metals using FDM process, and this is going to be the crux of our discussion today. So we call it, because it is extrusion based, so we call it extrusion based, and because we are printing metal, so we call it as extrusion based metal additive manufacturing process. Now, this particular kind of process, now I want to tell you that I'm also doing research in this area. So I want to tell you, this is not a process that I have invented. This process is something which is relatively new. It is not widely adopted, and this process came into existence something around 2017, 2018. So it is a very new process. So we need to understand that from where this process is actually derived. So this process takes its inspiration from metal injection molding process. Now, what is metal injection molding process? We are going to discuss it in the next slides. But I would like to read out this particular point, that one such process is the extrusion-based metal 3D printing technology known as MFF or FDMAT. So if you look into the research papers, researchers quote it with MFF, which is metal fused filament fabrication, or FDMAT, which is fused deposition of metals. I like to call it as extrusion-based metal additive manufacturing. Now, coming back to this point, that this draws its inspiration from metal injection molding process. I'm sure you must be all very familiar with what is an injection molding process. It is used for molding plastic parts, but in this case, it is used for molding metal parts. So before I explain to you that how you can combine FDM process for 3D printing metals, I would like to give you some understanding of how does metal injection molding works out, because until and unless you don't understand that how this MIM process works, you'll not be able to apply it for 3D printing of metals. Okay, so here is a flow diagram of metal injection molding. So because it is an injection molding process, it works in the similar fashion as the plastic injection molding process. But here, instead of plastic pellets, you have something else. So this something else, which is a complex recipe, because you want to because you want to mold metal powder, so of course there has to be some powder. It can be stainless steel powder, it can be titanium powder, any kind of powder. But this powder is not alone. So you need to make a recipe. You need to add some ingredients to it. So I will also come to the details of what ingredients should be there. But I can tell you right now that there has to be some kind of binder, there has to be some kind of thermoplastic elastomer, and there has to be some kind of surfactant. Now, why do I need binder? Why do I need thermoplastic elastomer? And why do I need surfactant? What are all these? So all this thing I'm going to explain to you in the next few slides. But for now, you understand that there is a complex recipe that is formulated. And in that complex recipe, the majority concentration is of metal powder. Now, what happens? This powder is basically mixed with some kind of plastic and some other additives. And this is being fed to the injection molding machine. Now, what happens in injection molding machine when the temperature is supplied? This powder does not melt, but the the thermoplastic elastomer or the binder, which are polymer-based materials, they melt, they become semi-solid, and when they are pushed into the cavity, they take the shape of the cavity. And the metal powder, it does not changes its phase. Rather than that, it keeps on being embedded within the particular structure. Now, once it has been injection molded, you will get a shape of that structure. Now, what happens, because you want a fully fabricated metal part, now you have to remove all these things that you are adding into the recipe together with the stainless steel powder. So if you're adding thermoplastic elastomer, that needs to go. If you are adding surfactant, if you are adding binder, all these things needs to go. But they need not to go in one single step, because if, let's say, if I make this particular part, if I have made this particular part where my all the plastic material has taken a shape and the powder material is sitting over there, if I try to remove everything in one go, what will happen? My metal powder has not bounded yet. They have not formed any bonds. So if I put it into a solvent, or if I do some kind of post processing, the polymer will go away immediately, but the metal powder, because they have not fused together, the part will be distorted, okay, or the part will collapse. So this is the reason that we have to go step by step, and in those steps we are going to remove a fraction of these additives at every step. So in the first step, what we do, we put it into a solvent. The solvent can be acetone, the solvent can be water, the solvent can be any acid, and this solvent is as such that it will eat away a specific material from this recipe. So it will either eat away your thermoplastic binder, or it will eat away surfactant, or it will eat away thermoplastic elastomer, whatsoever. But it will not eat away everything together, because if it will eat away everything together, then your part will collapse. So partial eating will be done and partial material removal will happen. This is also good for you, because when the partial removal happens, it creates some channels on the way. And when you will go to the next step, which is the thermal debinding process, pre-sintering, followed by sintering process. So in these two steps, what essentially is going to happen, you are going to put this debound part, into a tube type sintering furnace, where inert gas, something like argon, is being supplied. And what happens, the temperatures over here will be something around 1700 degrees or 1600 degrees, depending on the material that you are using. At those temperatures, the metal powders will start to fuse together, and whatever polymer you are adding, polymer will degrade and evaporate at that particular temperature. So of course, again, this temperature is not given in one single go. There has to be some cycle which is particularly followed. And once that particular cycle is followed, the polymer goes away slowly, and the metal powder keeps on fusing together, giving you a final part. This is the overall philosophy, and then you can of course do some post-processing operation after this sintering operation. These post-processing operation can be polishing operation, it can be hot isostatic pressing for increasing the density, for decreasing the density of the parts, so the parts can have more strength. That can be taken care of. And another thing which is worth noting at this particular stage is, because you are losing polymers at every stage, solvent debinding stage and thermal pre-sintering, thermal debinding and sintering stage, the parts are going to shrink. Okay, and this is something that we know. This is because the process is designed in a way, this has to be there. So this is not a problem for us. If we can map that how much shrinkage is happening, we can make our parts oversized in the initial design of the model. So this is the overall philosophy of metal injection molding process. I'll also spend a few more minutes talking about MIM, and then I will jump back to our FDM process. So here is some text that I have mentioned. So this takes inspiration from plastic injection molding, and in here, fine metal powders, particles, they replace the significant amount of plastic. Like I told you, it's not the metal alone, metal powder alone. There is a particular kind of recipe. So you mixed binder, thermoplastic elastomer, and surfactant to it, and each of these has a role to play. And we will talk about that when we'll talk about 3D printing or using extrusion process. But for now, you understand that this complex recipe is being formulated. Okay, and then it is being pushed through the injection molding machine, and a part is being formed. This part is called as the green part. Okay, and then it will be put into a debinding chamber, like I told you, where partial debinding happens, where the thermoplastic elastomer goes away using chemical debinding, and then it is being put into a pre-sintering stage in a sintering furnace. And once the entire sintering has happened, then the part that we get is called brown part. The brown part is finally sintered, giving you the overall metal part. Now this might be looking a little complex to you, so I have also incorporated a couple of videos. So let us look through these videos. I think after these two videos, everything will be crystal clear. So please pay attention to these videos that I am playing to you. They are showing the working principle of metal injection molding process. So here you see that you have put in the recipe, and it will be pushed through the hopper. It will go into this barrel, and then it will be pushed to the mold cavity. And in that manner, the shape of the part is being formed. Now this part is given its shape majority by plastics, and the metal powder is just sitting over there homogeneously in the system. Then you are doing debinding and sintering. Okay, so you have seen that the parts have shrunk and at different steps, and this the final outcome that you see on the screen. This is the final metal part, which you can polish, which you can paint, or which you can I mean, different other post-processing operations can be done on it. So coming back to our process, so what we thought that how we can combine this FDM process with this other process that I have shown to you, which is inspired from metal injection molding process. So what is the feedstock or the raw material for the FDM process? The feedstock or the raw material is this thing, which is the spool. So first of all, you need a spool, and of course you need an FDM printer. The steps will remain the same. The first step will be filament fabrication. So this is spool. So first question is that how you are going to make a spool out of it. So first you have to make a spool, and that spool will have a very unique recipe. Okay, and that recipe will have majority fraction in that recipe will be metal powders. So metal powders will constitute something around 75% or 80% by volume, and the remaining will be thermoplastic elastomer, binder, and surfactant. In the next slide, I will tell you what will be the utility of all these things. So somehow, let's say you have made this particular spool, then you have to 3D print parts. Many people, when I explain this particular topic, confuse with the fact that this particular thing, this particular extruder head where the nozzle is there and where temperatures are supplied, people confuse that are they going to I mean, is this nozzle is going to melt the metal powder? No, this nozzle cannot supply temperatures high enough to melt the metal powder. This is certainly not the aim. But this nozzle can supply temperatures high enough to transform the polymer which is present in the system. And this polymer could be anything. This polymer could be ABS, this polymer could be PLA, this polymer could be nylon, this polymer could be anything. any thermoplastic polymer. So what happens over here? So this particular feedstock, when it is being fed to the extruder head, when it goes through a nozzle, the nozzle supplies the head supplies the temperature sufficient enough to transform the polymer part, and then in layer by layer fashion, the part is being printed. And what about the metal powder? The metal powder is just sitting there as a filler somewhere into the system. Okay, so this is the first step. First step is of course the filament fabrication. The second step is 3D printing, which I just explained, and thereafter you have to take inspiration from the MIM process, and you do some solvent debinding, thermal debinding, and sintering process. So in the next few slides, I will explain to you that first of all how you can make the filament, and then thereafter how you can go through each and individual parameters to get the final metal part. Now, the beauty of this process, if you understand it carefully, is that now this will give you confidence that maybe tomorrow I can buy an FDM printer, and maybe if I understand how this particular recipe and how this particular feedstock is being formed, then my problem will be solved, because this printer will be something like 30,000, 25,000, and then I can put up my spool over here, and then I can print parts. So this will significantly bring down the cost, and at the same time, it will also make your structures lightweight. Why it can make your structures lightweight? Because you all know that in FDM process we have to give some infill patterns.
Sir, sorry to disturb. The slides are not visible, sir. The video
slides are not visible. Where are they stuck? Okay, thanks for informing those. Let me do that again. Sorry. Just give me a moment. Just give me. Are you able to see the next slide with printer?
Yes, sir. Yes, sir.
Okay. Now they are visible. Okay. Because I cannot see what is visible and what is not, so maybe you can tell me if something goes wrong. So you can see this printer on the screen. So I was talking about these 5 processes or 5 steps of this thing. Okay. Let me go to the next slide. So can you read materials for filament fabrication in the next slide? Can someone confirm?
Yes, sir. Yes, sir. It's visible, sir.
Perfect. Okay, super. So I was telling that what you can do, tomorrow you can maybe buy a cheap 3D printer, and maybe you try to understand that how feedstock is being formed, and once you make the feedstock and once you modify the extruder head accordingly, even you can 3D print metal using a cheap FDM printer. The first step will be that you have to make a filament. Okay, and this filament is the most crucial part, because even though I explain you all the theory, you might feel that it is very straightforward, but in principle it looks very straightforward, but in reality it is not that straightforward to make the filament out of it. And you will explain why I will when I will explain to you that how these things are being formed. But first, let me tell you that what are the different constituents. You already know from the previous discussion, the majority of constituent will be metal powder, because you have to make the part in metal. Now, this is something which is intuitive, that if you are using 80% metal powder, your shrinkage that will happen in the overall structure will be 20%. If you are using 75% metal powder, the shrinkage that will happen will be 25%, because the shrinkage that happens in the structure is basically due to the fact that all the other additives and all the polymer that you have used, that they will go away. So that is the reason shrinkage will happen. So metal powder will definitely constitute the majority of the part. Thermoplastic elastomer. Now, why do we need thermoplastic elastomer? You imagine that if, let's say, tomorrow you say that, sir, let us use 99% metal powder and only 1% other things. It will be extremely difficult for you to make a filament out of it. Okay, if you try to make a filament out of it, it will be extremely difficult. Why? Because the metal powder is a powder. Okay, it is a powder form. So unless and until I bind it with something and give it in a filament shape, it will be extremely difficult to push these powders out. 99% metal powder and only 1% other thing, it will not happen. Let's say if we choose something like 80-20, 80% metal powder and 20% other things. Okay, it might be possible that you can get a filament, but that filament will be highly brittle in nature because the metal powders, they are not bound together in the filament. So if they are not bound together and if it is highly brittle, it will be very, very difficult for you to wound it on a spool. You will not be able to wound it on a spool. When you will try to wound it, it will break. So you have to think in terms of, first of all, that you need to have some kind of flexibility. You need to provide some kind of flexibility to the structure so it can be wound on a spool. And secondly, when you are going to 3D print it, it is this thermoplastic elastomer which will be helpful in 3D printing. Metal powder will not 3D print in this case. What will be 3D printed is that thermoplastic elastomer. The metal powder will be sitting there in the structure just as a filler material. So thermoplastic elastomer, we need it for this purpose because this thermoplastic elastomer gives flexibility to your feedstock, and at the same time, it will also help you while 3D printing the part, because the parts will be printed in a layer by layer fashion, and the two layers are joined because of this thermoplastic elastomer, similar to plastic 3D printing. You will need binder as well. Now, binder is another kind of polymer. And why do we need binder? Because it acts as a backbone. Now, what is meant by backbone? Remember, I told you that we don't take away all the things in one go. First, you dip it into a solvent, and second, you put it into a furnace. So, at the time when I put it into the solvent, some part of it will go away, but some part will remain. Some part of polymer will remain, and that thing which remains, that is the binder, and that is why we call it as a backbone, because just like backbone, it remains over there, okay, allowing your structure to be sturdy, and that structure can be transported to a furnace where everything else which is there can be removed. Okay, so this is the utility of binder. There's another thing called surfactant. This you will understand when I'll explain to you that how the filaments are being made. So for filament fabrication, you need an extruder. In an extruder, there's a barrel, there's a screw, and then you feed things from hopper, and then they are pushed outside, and a filament is being formed. Now, because there is a lot of metal powder in it, the viscosity of system is very, very hard to manage. The viscosity will be very, very high. It will be very, very difficult to push the metal powders out of the extruder. So this is the reason you need some kind of additive, and those additives are called surfactants. So surfactants essentially help us to reduce the torque requirements during extrusion, decreasing the mixture's viscosity. Okay, and this mixture is which is powder, TPE, binder, and surfactant. So all these constituents you have to mix in a particular proportion, and after that you will be able to get a filament. So how a filament is made, this is what I was explaining to you, that you feed this recipe from a hopper, and then there's a screw. This is a filament extruder. This particular extruder is a single screw extruder. There are also extruders called twin screw extruders. I will show you in the next slide. And you feed everything over here, you give some temperature to it, and then a filament is being formed. And if it is not flexible, you will not be able to wind it, because when you are going to wind it, it will break very easily. So you need some kind of flexibility, you need some kind of flexibility, and that is why you add some additives. There are also other things that I have shown over here, compounding and material selection. They are not very significant at this particular stage.
तो फरीदाबाद दिल्ली होते हुए जाएंगे आप नोएडा होते हुए
then what we do compounding using twin extruder. So compounding using twin extruder, you have these two screws, okay, and everything is fed through hopper. Now thing is that when you are mixing this recipe in a hopper, when you're putting everything in a hopper, there's a high likelihood that when a filament is being formulated, in one zone there is a high concentration of metal powder, while in other zone there is no metal powder at all. So when a part is being printed, what will probably happen if you go ahead with this particular filament? In one particular zone there is lot of metal powder that is there, while in other zone there is no metal powder at all. So when you put it into the solvent debinding chamber and when you put it into a sintering chamber, what will happen? Because there is no metal powder over here, so this part will go away and your structure will become distorted like this. So then it is very, very important that what we do, we make sure that in the filament, the distribution of metal powder is uniform. And the strategy that we do for this particular thing is that once we put everything into a hopper and once we make a filament, you pelletize it. You cut that filament and collect those pellets, and then you feed it back into the hopper. You repeat these steps at least 6 to 7 times till the uniform proportion is being obtained. Okay, so this is an iterating method that I have explained over here. And in that manner, a filament is being formed. Now, of course, there will be effect of many things in this, that what is the morphology of powder, what is the size of the powder, what is the shape of the powder, how much powder you are using. Okay, all these things have some or the other role to play into the picture. So, like I told you, read this third point. A feedstock with high powder content produces filament with high inhomogeneity, making them highly brittle. Okay, if there is a lot of powder and if there is a very little polymer that you have added, your things will become very, very brittle. Okay, for the final part to shrink less and have a high density at the end of sintering, having the maximum powder percentage in the feedstock is necessary. So if you read these 2 points, these 2 points are contradicting in nature. In second point, what I'm telling you, that if you want very less shrinkage, use maximum powder. While in third point, I'm telling you that if you use maximum amount of powder, what will happen? It will make the filament very much brittle. So that is the reason that you have to make a good balance of these two things. There is an optimal concentration of powder that you need to find out, and that you have to use for your filaments. Okay, the rheology is of course very, very important. The viscosity is very, very important to look into when the filaments are being fabricated. Okay, now you may ask that is it very straightforward that tomorrow I buy a cheap 3D printer and let's assume that we make this a spool somehow, and can we start printing the parts? In principle, yes, you can start printing the parts, but you will face a lot of difficulties. If your nozzle or the extruder head is not appropriate, what will happen? This nozzle will keep on getting clogged again and again. This is one thing. Second thing, if it does not get clogged, it will be worn out very easily. You see, this when you are printing polymers, there is no metal in it. Okay, I'm just talking about FDM printing. When you are printing polymers, when you're printing in ABS, when you're printing in PLA, there's no metal powder in it. So it doesn't matter whether this nozzle is hardened or not. But in this particular case, there is metal powder in it, and this metal powder will again and again rub against the head of the nozzle, and because of that, your nozzle will be worn out very, very fast. So you need to use something like a very hardened nozzle, a very special kind of nozzle you have to use. But other than that, you don't have to modify anything in the structure. A good thing about this particular structure is that you can also do hybrid additive manufacturing. So you can do additive subtractive manufacturing together. So while you are printing the part, at the same time there can be something like a milling setup that can be embedded, and this milling setup can mill out the parts which are not desired, and then again the extrusion can happen on the top of the part. Okay, so you can do this hybrid additive manufacturing, additive subtractive manufacturing, and then once this thing happens, you put it into a solvent bath, do solvent debinding, and then you do the sintering, thermal debinding and sintering, and then you get the final sintered part. So this is another philosophy that you can look into. Now, I told you in the a few slides ago that this is not something that I invented. But our research at IIT Mandi is that we are combining everything end to end, which means that we have developed the techniques with which, so we have the knowledge with which we can make the recipe ourselves. Because we understand that what recipe we are making, we can extrude it comfortably, we can 3D print it, and because we know the constituents of the recipe, then we can also comfortably debind it. Because in debinding, you are going to choose a solvent. If the supplier does not tell you that what he or she is mixing into the filament, how you are going to choose the solvent? You cannot decide whether you have to choose water as a solvent, or hydrochloric acid, or chloroform, or anything else. So unless and until you understand the constituents, you will never be able to choose the solvent on your own. So because we design our own recipe, so we understand that what solvent is required, and we do debinding ourselves. Thereafter, we also have the sintering setup, and we sinter the things, and then in that manner the parts are being formed. Okay. So a couple of my PhD students are working in this area on extrusion-based metal 3D printing. We are one of the very, very few groups in India who are working on this particular technology. There are not many groups who are working on end-to-end solutions, who can say that they can design the filaments also, and they can also sinter themselves. They cannot do that. Okay, so this also makes our research very, very unique in nature. Yes. So coming back to the topic, once you have done this, then you put it into the debinding. You might also say that, sir, what is the need of debinding it in a solvent? We can put everything directly into the furnace, and that will help us. I mean, the sintering cycle can evaporate everything, and then the metal powder will join. That is also possible, but that will create some problem. So you see, if the binder is not removed completely, what will happen? You will see blisters like this. The reason is because you have not done a proper solvent debinding. What see, imagine when solvent debinding is happening. So what essentially is happening? Pores are getting created. Okay, and these pores allow as the escape route of everything else to come out and vaporize when the final centering is happening. If these pores or if these channels are missing, what will happen? Everything which is inside, it will try to vaporize, and because it will not see any escape route, so you will see blisters like this, which is a very common defect in this particular type of process. I've also made some very nice figures over here. So you see that this is the green part that we get, and then we put it into a solvent, and the solvent eats up the material very slowly. So you see, after 4 hours debinding, 8 hours, and 12 hours, what is happening? You see white spaces are getting formed. Okay, and these white spaces are essentially the channels that are getting formulated. So in the next step, whatever remains, the reddish orangish thing that you see over here, whatever that thing remains over here will be evaporated and will be pushed out through these white spaces, these escape routes. So when I will put it into the sintering furnace, in the next step, you see everything has come out, and you get a structure. And at the same time, you see this necking phenomena is also happening in thermal debinding, where the powders are coming together and they are joining together. Now you can certainly say that, of course, this process looks like that there will be some porosity. Yes, there will be some porosity in the system that will remain, and that porosity is comparable to the porosity that you get in LPBF process. But there are ways to tackle with that porosity. We are also working on post-processing methods. We are working on hot isostatic pressing, which is very, very good technique with which you can control these porosities that are appearing over here. Okay, so like I told you that sintering will happen at a very, very high temperature. Sintering is happening at 1300 degrees centigrade. I've written here 1300 degrees because I'm talking about stainless steel 316L. But if it is any another material such as titanium or any Inconel or anything else, this temperature number will certainly change. But it is certainly something above 1200 degrees, 1300 degrees. Okay, shrinkage definitely happens. And like I told you, that whether you are using fine powders, coarse powders, or if you are using irregular shape powders, all these things have a role to play. And this is also written in third point. The use of fine powder leads to higher diffusion rate, more shrinkage, and hence provides higher relative sinter density when compared to large powder. So today we are not talking about what will be the influence of powder size, powder particles, all those things. But today I'm trying to give you an overall philosophy and an overall summary of how things can work out. Okay, so here I have another fact that I have mentioned over here, that how you can control the density. Okay, so in that manner, you will be able to get the final part, and this final part will have some part porosity that will remain. So you can see over here that sintering is happening. The powder particles are coming together; they are fusing together, and in that manner, the final part that is being formed, there is no polymer that exists over there. There is no thermoplastic elastomer. There is no binder. There is no surfactant that is present. The only thing that is present over here is metal. Okay, so this is the overall summary. Okay, so I still have a few more slides to talk about, but I hope you have understood the overall philosophy and how you can utilize an FDM printer for printing metal parts. So we have published a very good review paper on this topic, which is published in Composites Part B Engineering. You can download this review paper and you can read about everything that I have talked in today's slides. Okay, so this is one thing. These are the references that I have used. Okay. Another important thing before I close my today's talk is this particular thing. So I am also organizing a course on design thinking and product development methodologies using additive manufacturing process at IIT Mandi. This course will be organized in the month of March. So this is after Holi, from 9th to 14th March 2026. It is fully residential program, and the beauty of this program is that you don't have to pay any registration fees, you don't have to pay for accommodation, and you don't have to pay for food. All these things will be taken care by us. So this is fully sponsored course. You only have to bear the cost of travel. I would say this is a certainly very, very good opportunity to visit IIT Mandi. You can come here, you can stay with us for a week, you can learn about different product design methodologies, and you can see our lab and experience the additive manufacturing process. So if you are interested, okay, before that, what is the eligibility criteria? So not everyone can participate, only the faculty members. So if you are a faculty member who is working in any university or college, they are allowed to participate in this course and they will be sponsored. Here I have written all the salient features. It will be 6 days duration, 36 hours, and it will have 24 lectures and everything about things. And at the end, there will be an exam and a certificate will be issued to you. So if you are interested to participate in this, application deadline is 20th February. And because we have a very, very limited spots, because it is a sponsored program, I suggest you that if you are interested, please apply as soon as possible. Don't wait for the last moment, because there's a high likelihood that the seats will go away. You can take a screenshot of this particular slide, or you can scan this particular QR code. It will give you a course brochure. That particular course brochure has a link at the end. So at the end, you will see that how you can apply for this course. You have to fill out some forms, but everything information is given in this particular brochure. Okay, so that is all from my side. This is the last slide. You can also note down my email and phone number. Feel free to write to me on WhatsApp or call me. This is my WhatsApp number as well. If you want, we can connect on LinkedIn. So scan this QR code to connect on LinkedIn with me. I'm very active on LinkedIn. We'll also publicize this on LinkedIn in the next couple of days. So you will see all the information over there. This is my research group. And with this, I thank you very much for patiently listening to this presentation. And now we can take some questions. Okay. Thank you very much. Dr. Das, are you there?
Yeah, if participants has any questions, you can ask. Yes.
Dr. Pratik, this is Dr. Puneet Mangla. Good evening. Thanks a lot for a very interactive and this informative session.
Yes. Good evening. Thank you.
It was excellent, really excellent. Actually, my few of my students, they were working on some of a project similar to that of yours. You have explained, that is extruder, filament extruder. So I mean, the screw of the extruder, everything have been designed, but ultimately the one point which you raised was very correct, that the clogging of the nozzle at the end, it very oftenly it happens, right? So how can that be avoided? First, second is the temperature difference between the nozzle and the extruder that counts for this clogging also, and how much?
My question to you, counter question to you is, you mentioned that you have some extruder, so you are basically, I mean, using extruders for
Your voice is cracking.
reinforced.
Your voice is cracking.
Be able to hear me? Fiber reinforced.
Hello.
Yes, I can feel so. Just give me a moment.
Yeah.
Yes. So I think there is some lag now. I think it is fixed. Are you able to hear me
Yeah,
properly?
it's clear. Yeah, it's clear now.
Hello?
Yes, it's clear
Yes.
now.
So my question to you is that yes. Okay. So my question to you is that most of the people, they use these extruders for making feedstock with fiber reinforced things. For example, glass fiber reinforced PLA, or some people, they put in sawdust or banana peel or whatsoever. So if you are using something like that, then that becomes a different query. Because they are the size of the fiber that you are using, whether you are using short fiber or what is the constituent, how it is being mixed. They can, of course, if they are not uniformly mixed, they can clog the system very easily. But if you are putting something like particles, and if it is not being pushed out well, then it can definitely clog the system. What you can do is that you can look into the design of the extruder. Typically, the extruder has got different temperature zones, so you try to control that
Definitely.
zones, and the nozzle from which everything is being pushed out, try to take that nozzle as thick as possible. So don't keep it as something like 1.75, try to make it something like 2.85 mm. We typically use something like 2.85 mm nozzle for extruding the thing. Try to do that. That is the thing that you can try to play with. And of course, the
That is one
temperature.
part, like,
Yes.
if we increase the size of the nozzle.
Mm-hmm.
But if in case we want to, make the filament of the size that is required, maybe 1.75 as you mentioned, or 2,
Yes.
so it's getting clogged. Definitely the temperature difference counts there, and I could understand there. And the students, they were using PLA as a material, of course.
Mm-hmm. So what you are
So
adding in PLA? Are you only using virgin PLA, or are you
yeah,
also
virgin
mixing?
PLA.
Okay, then it should not be a problem, because if you're using only polymer, then there could be some problem with your extruder itself. Because you mentioned that you have developed an in-house extruder. We also developed an in-house extruder. So in that, a lot of things come into play. For example, what is your length of the extruder, and what is the temperature in each zone that is being put into?
Temperature, yes, definitely.
Yes. So yeah, but PLA, in my understanding, is not very difficult to extrude. PLA can be extruded very easily. If you are facing problem with that this implies that there is some problem with the extruder itself. So if you are facing problem with extruding PLA only, then you will face more problems if you add something else to it. Okay,
Yes,
so try to fix that. Then we can take a separate discussion as well. You can connect with me later on, and I can guide you in more detail how you can
sure,
fix that.
sure,
Okay.
Thank you so very
Th-
much.
Thank you. Anybody else would like to ask anything? I'm reading all the comments. Thank you very much for liking the session. Any more questions? Anybody would like to ask anything? If not, I would strongly recommend you to please join our residential course that I'm offering in March. Please connect with me, and if you have any queries, just write down to me, or on WhatsApp or LinkedIn or wherever.
What is the time period for that
It
workshop?
is it is in it is in March, from 9th March onwards, for 1 week.
1 week. Can the students also participate in that?
No, only the faculty members. So if
Only
you are a
the-
faculty member in
right.
any institution, government, private, whatsoever, you can participate.
Okay. Thank you.
Sir, please give me your contact number.
So I have put it on the slides, but I can write it in the chat box as well.
Yeah, sure.
So this is my phone number, and let me write my email. Yes, so I've mentioned both my email and my phone numbers, and then you can also connect with me on LinkedIn. Please don't follow me, just send the connect request. So if I'm not available on phone, you can at least write to me on LinkedIn. I'm pretty active on LinkedIn.
Yeah,
So
sure.
yeah, these
Thank
are
you, sir.
all the ways to reach me out. Okay, and if there is any
Thank you.
possibility of any collaboration, just let me know. I will be happy to support you all.
Sir, actually, we are checking the link for the registration in the IIT Mandi, but I am unable to get that link over there.
Okay, the QR code is not working. Is that what you mean?
Yeah, actually, I don't get the QR code.
Okay, just give me a moment. Thank you for raising this. I will quickly paste the link here. Just give me a moment. So I have pasted a Google Drive link as well. You can just click on that Google Drive link and you will be able to see the course brochure. Okay. Shirish has also shared over here. Thank you, Shirish, for sharing.
Thank you so much, sir.
Okay. Thank you very much. Thank you very much for attending this session.
Thank you, sir. Thank you for your informative session. To conclude this session, I invite Mr. Aziz, Assistant Professor, Bethlahem Institute of Engineering, to deliver the vote of thanks.
Good evening, everyone. On behalf of Department of Mechanical Engineering, Bethlahem Institute of Engineering, I am honored to deliver the vote of thanks for our 6-day faculty development program on additive manufacturing. First and foremost, my heartfelt thanks to our Chief Patton, Director, Principal, Dean Academics, Convener, Program Coordinator for their continuous support for approving resources and for empowering the faculty organizer to run this FDP smoothly. Now, I gratitude to our resource person for this session, Dr. Pratik Saxena. Thank you for the insightful session on additive manufacturing. Thank you. Once again, I thank you for all participation and who have joined each. Thank you.
Thank you very much.
Thank you, sir.
Sir, one thing, when I tried to register on that, it is showing that participant already registered, but I haven't done it.
Okay, Shirish, what you can do, you can write to me separate. I mean, Shirish is asking a question, right? Shirish, you can write to me on WhatsApp and we can connect over there and we can discuss it separately, okay?
Okay, thank you.
Okay, if you have any troubles, just write to me. Also on the drive, the link that has been shared on the last page, there's an email ID that is given. So that email ID is for any help and support that you can ask for. It is not my email ID, but it is the email ID of the team that is organizing. I'll also put it over here. So if you have any queries, you can just write to these email ID, any technical difficulties that you are facing, if you want NOC format or whatsoever, just write to them. They will be able to answer. And if your query is not resolved, just write to me. Okay. So it is pasted in the chat box, mmttp@iitmandi.ac.in. Okay. So thank you very much.
Okay, thank you, sir.
Ajish, can we close the session now?
Okay, sir.
Okay, sir. Okay.
Thank you. I'm leaving now. Okay. Thank you. Bye-bye. Good night.